In today's video, we're going to look at section 5.6, which is further counting techniques. This brings together some of these counting techniques that we have looked at within chapter 5, using all of these ideas of permutations, combinations, factorials, etc. And when you see a problem, kind of thinking logically about how you would solve it using those ideas. I'm going to take some examples from the textbook and homeworks, etc., in order to show you some of the problems that you may come across. So the first one, this comes from the textbook, and it's looking at tossing a coin. This is a classic example that you will see. In this experiment, we're going to toss the coin 10 times. And we're going to look at outcomes that involve heads and tails and a certain number of each. Okay. First problem that we're going to look at is how many different outcomes are possible. Okay, so that's asking how many different combinations can I have of heads and tails. Second problem is going to see exactly how many of those outcomes have exactly 4 heads. And then the last two parts of this problem that we're going to look at are going to be kind of linked together. First one's going to ask how many outcomes have at most 2 heads. And then the last part is going to be how many outcomes have 3 or more heads. Okay. So the first problem asks how many different outcomes are possible. Okay. Let's think about exactly what outcomes there are. So we know that there are 10 possibilities here, 10 different trials that we are undertaking here. So each time we toss the coin, that is seen as a trial. Okay. And each time we can have heads or tails, heads or tails. Okay, for all 10 of these. So each one has 2 outcomes. So by the multiplication principle that we looked at in section 5.4, in order to find the total number of possible outcomes, all I need to do is multiply the number of outcomes from each one of our experiments, which will give me 2 to the power 10. Okay. The next problem looks at how many outcomes have exactly 4 heads. Okay. This comes down to our permutations and combinations. Okay. When we did that, we said that permutations always looked at things where the order mattered. In this case, it doesn't matter which order the heads or the tails are in, etc. Okay, I'm not looking at like a first, second, third place example. So in this particular problem, I can use combinations. Okay, I want to see out of 10 trials, 10 different times of tossing this coin, how many times I can get exactly 4 heads. Okay, so when we looked at combinations, for that problem, I would be looking at getting exactly 4 out of 10, which would be the combination where n was 10 and r was 4. So that would be 10 factorial over 4 factorial times 10 minus 4 factorial, which is 6 factorial. And if you go ahead and calculate that, it comes out to 210. So there are 210 different possibilities where I have 4 heads and therefore 6 tails, as the order does not matter. The next part of the problem looks at how many different outcomes have at most 2 heads. Okay. Well, if you have at most 2 heads, that means I either have no heads, 1 head, or 2 heads. So I'm adding together in the same fashion that I did here the combinations where I have no heads, 1 head, and 2 heads. And I will add each of those together, and that will give me the total number of ways that I can have at most 2 heads. Okay, so it will give me the number of ways I can have no heads, the number of ways I can have 1 head, and the number of ways that I can have 2 heads. And therefore, if I add together the number of ways, that will give me the number of ways that I have at most 2 heads. So if you figure those out using the combinations formula or by using your calculator, it turns out that that comes to 1 plus 10 plus 45, which is 56. So there are 56 different ways where I can have at most 2 heads. The last part of the problem looks at how many outcomes have at least 3 heads. Okay. A couple ways that you can do this. You can either look at the outcomes where you have 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads, and 10 heads. So that would be the combination of having 10 things and you're choosing exactly 3, plus the combination of 10 where you choose 4. And you're going to keep going through all of these up to having 10 heads. If you did that, you should come out with 968. But that is a very long calculation. It's actually easier to go another way around this. If we go back to what the problem asked, we're looking at how many have 3 or more heads. My previous problem looked at how many outcomes have at most 2. If I add together the outcomes of these 2 problems, I should end up with the total number of outcomes that are possible. So I know that the number of outcomes that have at most 2 heads plus the number of outcomes that have at least 3 heads should equal 2 to the power 10, which is 1024. So I could also have done this by taking 1024 minus the number of outcomes that have at most 2 heads, which was 56. And again, I would end up with 968. So sometimes there are shortcuts to these, particularly if you have a previous part of a problem where you've already figured something out. But in particular, whenever you have one of these problems where it would involve adding together a bunch of these combinations, sometimes it may be easier to look at the outcomes that you are not asked to look at. So in this case, if we're looking at the number of ways that you can have 3 or more heads, look at the number of ways that you can have at most 2 heads. That means you only have to calculate 3 combinations and not a bunch of them like we have here. Okay. So I would highly encourage you whenever you get one of these problems to look at that. But like I said, we're using combinations here because we don't have to worry about the order of the heads and the tails. So we know that we are using combinations because we are taking a certain amount, in one of these examples. In this example here, we were taking exactly 4 out of 10. So how many ways can I take 4 things out of 10? I'm going to use combinations because I don't have to worry about their ordering. If I did have to worry about their ordering, I'd be using permutations here. But because I don't have to worry about their ordering, I'm using combinations. So whenever you get one of these problems, that's what I would encourage you to look at. Number one, are we looking at combinations or permutations? And then see with some of these, if you had to add together a bunch of these combinations, is there a faster way to do this, like I did here, where I took the total number of outcomes and then subtracted a value where it would be slightly smaller and slightly easier to calculate than one of these larger values? Okay, the next example that we're going to look at, this one has a few different ways that you could approach it, but I'll show you the way that I did this. And this is actually a homework problem. You may get slightly different numbers, but it's the same idea. And it says that a telemarketer makes 15 calls. And we want to know in how many ways can the outcomes of the calls be that you make 3 sales out of the 15, 8 no sales, and 4 no answers. Okay, so in some combination, we need 3 of the 15 to be sales, 8 of the 15 to be no sales, and 4 of the 15 to be no answers. So the way that I approach this is to kind of systematically go through it. So first, look at the number of ways that we can have 3 sales out of the 15 calls. So because the order of those does not matter, it doesn't matter where they land, I use a combination. So I've looked at in how many ways can we get 3 sales out of the 15 calls, which is the combination where n is 15 and r is 3. So there are 455 ways that we can do that. After we've done that, there are 12 other calls. Okay, we know that 3 of them are sales. Now I want to look at, of the remaining 12 calls, how many ways can I get 8 no sales out of those 12 calls? So out of the remaining 12 calls, I'm going to look at the number of combinations, the number of ways that I can get 8 no sales. And that ends up being 495. That then just leaves me with 4 calls. And I want to look at in how many ways can I get 4 no answers, so 4 of a particular outcome out of the 4 remaining calls. Well, there's only one way of doing that. Okay, there's only one way that we can get 4 of one specific outcome if we've only got 4 things left, and that is if every single one of them was a no answer, every single one of them was that particular outcome of no answers. Okay, once you've done that, you can then multiply all of these together. Okay, you have your first choice, your second choice, and then your third choice. Okay, so we can treat each one of these as like its own trial. Okay, so you've got 3 different choices that have to be made. How many sales you have, how many no sales you have, and how many no answers you have. And then multiplying those together will give you the number of ways in which you can have all of these things put together by using that multiplication principle. So it's basically like treating it as 3 different choices and then multiplying them together. The next problem that we have, again, this is from your homework problems, but there is a very similar example in the textbook, which is also a classic probability example that you will also see when we go through that section. And in the textbook, it looks at coloured balls in a container and seeing like what happens, how many of each colour you can pick out, etc. And that's a very classic probability problem that we'll come across. But at the moment, we're looking at the outcomes. And this time we have a bag of 11 apples. 3 of the apples are rotten and 8 of the apples are good. And a shopper selects 4 of the apples from the bag. First, we want to know how many different samples are there of these good and bad apples when we pick 4 of them out. Okay, so again, the order that we pick them out does not matter. It doesn't matter whether you pick out rotten ones first or good ones first. The order of them does not matter, so we're using combinations again. And out of the 11, we're picking 4 of them. Okay, the shopper picks 4. So the combination where n is 11 and r is 4 gives you 330. So there's 330 different ways that I can pick out good and rotten apples when I pick out 4. How many contain all good apples? Okay, so when the shopper goes and picks out 4 apples, how many of those samples, how many of the 330 different outcomes that we saw, how many of them have all good apples? Okay. When we think about this, we know that there are 8 good apples in the bag. So we want the number of ways that we can pick 4 good apples out of the 8. Okay? We don't need to worry about the bad apples in this case. We are just looking at the good ones. We want to know in how many ways can we pick 4 of the 8 good apples. Again, the order that they're picked in doesn't matter. So we're looking at combinations where n is 8 and r is 4, which gives me 70. The next problem looks at how many samples contain at least 1 rotten apple. This kind of goes back to our previous example because there's a couple of ways that we can do this. The way that I did this was the shortcut way. So I said, okay, we know that if a sample contains at least 1 rotten apple, okay, remember we pick out 4 apples, it can have 1 rotten apple, 2 rotten apples, 3 rotten apples, or all 4 of them are rotten. The only outcome that we are not interested in here is when there are no rotten apples. Because if there's at least 1, then we don't need to worry about the case when there are no rotten apples. That means that I don't have to worry about these 70 outcomes that we have where we have all good apples. So out of the 330, I can ignore those 70 outcomes. And that means that the other 260 of the 330 must contain at least 1 rotten apple because we've got rid of all of the outcomes where we have all good apples, which means no rotten apples. So I kind of went the shortcut way with that one. The other way you could have done it is by using the multiplication principle. So what you could have done is said, okay, I want to see if out of the 8 good apples, if I picked 3 of them, and then out of the 3 bad apples, I picked 1. So I've still got the 4 apples that I picked out, 3 plus 1. I've picked out 3 good apples and 1 rotten apple. Okay, choice 1 and choice 2, I've multiplied them together, and that gives me the number of outcomes where I have 3 good apples and 1 rotten apple. Then I would have to add on where I've got 2 good apples and 2 rotten apples, and then 1 good apple and 3 rotten apples. Okay. In this case, we don't have to worry about 4 rotten apples because we've only got 3 rotten ones in the bag. So I would use that multiplication principle to figure out each one of these outcomes where I have 3 good, 1 bad, 2 good, 2 bad, and 1 good, 3 bad. Use that multiplication principle and then add them all together. So that is a longer way of doing this, but it is another way of calculating it. So I would go the simpler way if you could. Okay, this last problem that I'm going to look at, again, there's different examples in the textbook. I think this one actually comes out of your homework. What we want to look at here is license plates where we have 2 different letters followed by 3 different digits. Okay, so a license plate here is going to have 2 letters and then 3 digits. How many of these license plates have letters that are in alphabetical order and numbers that are in increasing order? So I want my 2 letters here to be in alphabetical order, and I want my 3 numbers here to be in increasing order. There is a very similar example to this in the textbook. So once I've got this information, what I want to do is I'm going to line up all of my letters and all of my numbers in alphabetical and increasing order. So I'm going to line up A through Z in alphabetical order, and I'm going to line up 0, 1, 2 through 9 in increasing order. Once I've done that, I know that I have 26 letters here. They are in alphabetical order, we've just lined them up A through Z. Okay. I want 2 of them, but in order. The way that I would actually go about this, which is a slightly easier way than trying to deal with permutations and making sure they're in the right order, etc. I want to pick 24 out of the 26 to remove. I want to see how many ways can I remove 24 of the 26 letters. Okay? And the answer to that is by using combinations. It doesn't matter what order, therefore, I remove them in, as long as 24 of the 26 are removed. So I can look at the number of combinations where I've got 26 letters and I remove 24 of them, which is 325. Then I've got the numbers 0 through 9, so there's 10 digits. I need 3 of them in that order. I'm going to look at the number of ways that I can remove 7 of them out of the 10. Doesn't matter what order, therefore, I remove them in, as long as I have removed 7 of them. And that will give me 120. I have my first choice, which is by looking at the letters. My second choice is looking at the numbers, so I therefore just multiply these 2 numbers together, and that tells me that there are 39,000 ways in which I can have the letters in order and the numbers in order. So sometimes with these, the easiest way that you can do it is by lining everything up and then seeing the number of ways that you can remove those particular elements from your increasing line. Okay, there is a very similar problem in your homework where you look at family members lining up in age order and seeing how many ways that you can have a certain number of them in age order. Again, I would look at the number of them that you can remove. It's way easier than trying to deal with the number of permutations, etc., and looking at the order. It's just way easier to say, well, there's only one way that they can be in order. How many ways, therefore, can I remove a certain number of them once they are in order?